So this is where we left the last video, and it's a good place to start again. I just keep on repeating these things down here, that once lymphocytes have gone through their education processes, and once they are mature and prepared to activate, they will wait, possibly forever, until they become activated in a very specific way. They do nothing except wait. That is important. So we'll come back to that. What is the education process? Well, before I look at that, I want to remind you of the main thing, which is that each lymphocyte has one receptor, 100,000 copies of it, just one. So each lymphocyte can only respond to one thing. And our body has no way of knowing what that one thing is. That receptor was randomly generated by reshuffling the DNA in this cell. So all its descendants, if it divides, will have the same receptor, or even a better version. But this cell, this lymphocyte, its receptor has no relationship to the receptor on a different lymphocyte that isn't part of its lineage. That's an important thing to remember, right? Because our body has no way of knowing what this receptor detects. As far as we know, this might detect collagen, and we do not want to set up an immune response against our own collagen or our own myelin. But as far as we know, that's what this detects. There's no way the body can predict what this is going to detect. So education helps. This education process partly helps us with that. We just test, what do those lymphocytes respond to? We start by seeing if they're going to respond at all to antigen presentation via MHC. Most of them don't respond the way they should, because it's a very complicated process. It's way more than what you would see in a micro class or an A&P class. So most of them don't respond adequately, and we just kill them. That's it. We recycle them, make new cells, try again. What's left over? The cells that are capable of responding, almost half of them respond to self-antigens. If we present them with collagen or myelin or something, they respond to one of those. That means these would, if we deployed them into our lymphoid organs, they would start autoimmune diseases. And so we don't let them do that. As soon as we see that they are going to respond to self, we kill them. So they're gone. So of the starting population, we end up with 5% that are mature and educated. They've gone through this process. So we call them mature. And then we call them naive because they haven't been activated yet. They're just waiting to see if they should be. But 5% of these end up as mature, naive T cells. And so they're just going to wait and see if they are lucky enough to be activated someday. B cells have a similar process, but T cells, it's the clearest and simplest. So I'm only going to show it in T cells. You can just assume B cells have a similar process. So what education does is it removes all the lymphocytes that have self-recognizing receptors on their surfaces. So that the idea is this process removes any lymphocytes that could participate in an autoimmune response. Without this, our immune systems would kill us. It's as simple as that. Okay, so then what happens after education? They wait, okay? They wait. They sit in our lymphoid organs and do nothing. So primary activation is what happens when we activate them. So let's look at B cells because they're easier to draw, and this is a simpler process. When a B cell is activated, when it detects its epitope for the very first time, so this is the first time this lymphocyte has ever detected the epitope it's designed to detect. This may be the first time the body has ever had that epitope in it. So that first time, it will activate. It will go through what's called clonal expansion. I don't know if I have that on here. Oh yeah, clonal expansion. That means it's going to divide many times, and its daughters are going to divide many times. And some of the resulting cells will become plasma cells that make antibodies. Remember, we're looking at B cells, B lymphocytes. So if they activate, they become plasma cells and they make antibodies. Others will become B memory cells, memory B cells. They will wait for the next activation. So this would be what we would hope to happen during vaccination. When a protein from the vaccine finds the lymphocyte that recognizes it just randomly somehow, and that lymphocyte will go through clonal expansion and make plasma cells that make antibodies against that protein, so antibodies against the vaccine, and then memory cells that will accumulate in the tissues and be ready to quickly mount a response if we ever see that thing again. So memory cells are going to wait for that secondary activation, and they're going to be faster than the regular original lymphocytes were. So again, if we have that primary activation, that's like when we see the vaccine or when we first get infected by that version of the common cold or by influenza. We get this activation, and one of the products of it is a bunch of memory cells. So the second time we see it, we start with a much bigger population of starting cells that all respond at the same time. And that they are able to much quicker make a whole bunch of plasma cells, and their plasma cells are programmed to make a whole lot more and more effective antibodies. So that secondary activation is faster and more vigorous. So this is what we get the first time we're exposed when we have regular lymphocytes that are mature and naive, and we only have one of each type. Well, that one gets exposed, and eventually its descendants start making antibodies. But that could take the better part of a week. So if you think about, like, how long does influenza last? If you ever got the flu during one of the outbreaks, how long does the common cold last? The common cold might last 2 or 3 days. Influenza might last 5. That's how long it takes for the adaptive immune system to really take over. But then the next time you get exposed to that, you've already built up memory cells that immediately start the immune response. And so you might feel sickly for a day, but by the second day, you have a strong enough immune response from all those T memory cells and B memory cells that all got activated at the same time. They have all done what they need to do, and you have tons of antibodies and tons of cytotoxic T cells running around doing their jobs, and that stops the second disease from happening. So you had the infection, but the disease won't happen because the immune response gets in front of it. So primary activation is slow and steady. Secondary activation is fast and good enough to prevent disease. When lymphocytes are activated, it begins really with T cells being exposed to their antigen or epitope for the first time. I mentioned B cell activation a few slides ago, and what I showed you was the simplest version of B cell activation, but not even the most effective one. To really get a full antibody response, T cells have to be involved. They have to give signals to B cells. And so a real immune response has to get started by activating naive T cells. And so that activation always happens through the MHC systems. The major histocompatibility complex systems are what cells use to communicate with T cells. So all nucleated cells use the MHC-I system, or they're all able to use it, and they use it routinely. They show T cells whatever proteins are in their cytoplasm. and we'll come back to this, but this is kind of the anthropomorphic idea. I found this protein in me. Is this what you're looking for? That's what they would say to a cytotoxic T cell. Using this system. That's what this system allows them to do. Specialized cells use the MHC-II system, and they use it to display things they have brought in from outside. So things they've found in vesicles in their phagolysosomes or from their membranes. And they use these to display, to communicate with CD4 T cells. And so the different cells that do this are really dendritic cells, macrophages, and B cells. And all of them are saying, I brought in this protein. Is this what you're looking for? That's really the question they ask using their MHC-II, is I ate this. And in the case of a B cell, what it actually does is once its B cell receptor has bound its antigen, it brings it in through endocytosis and digests it so that it can show it to a T cell. And so dendritic cells and macrophages are going to use phagocytosis. Dendritic cells are also going to use pinocytosis and other processes to bring in proteins. And all of them will be displayed using MHC-II. So a dendritic cell, for example, will patrol epithelial layers and see if anything crosses them. And it will just take up any random proteins it can find, and it will take them to the nearest lymph node where it will show them to T cells and see if any of the T cells recognize them. And if they do, those T cells will activate. Dendritic cells activate T cells. So let's look at sort of how this all fits together. We'll start with the MHC-I, and we're just going to look at an interaction between a typical nucleated cell and a cytotoxic T cell. The idea here is that this cell has no way of knowing if it's got a tumor or if it's cancerous. It has no way of knowing if it's infected by a really clever virus. So what it's always going to do is put random cytoplasmic proteins on its MHC-I system, and it's going to display that on the outside of the cell. A cytotoxic T cell is going to look at it, and it's going to ask, does my T cell receptor fit this thing? If so, this cytotoxic T cell has found the thing it's looking for, and it knows this host cell is infected by something or is abnormal and needs to die. And this cytotoxic T cell will kill this cell. The other piece of this puzzle is the CD8 co-receptor. That stabilizes the interaction between MHC-I and the T cell receptor. So the cytotoxic T cell is asking, do you have the protein I was designed to see? And this cell is asking, is this protein in me the one you are designed to see? And if this is a virus that's causing a major infection in the body, it's likely that some of the cytotoxic T cells are running around looking for that exact thing. And if that's the case, this cell will kill this cell. And this virus factory will stop making new viruses. So that's what this says. Most of the time, though, our cells are not infected with viruses. Most of the time, our cells are not virus factories, and so they show random self-proteins. And cytotoxic T cells don't recognize them, so they don't kill the cell. We're going to look at CD4 and MHC-II in a minute. This is a useful thing to keep in mind. It's the rule of 8. It's when you're trying to remember, does CD4 go with MHC-I or MHC-II? 4 times 2 equals 8. 8 times 1 equals 8. So anyway, there you have that. I'm going to give one more example, And then we're going to stop this video and come back and look at putting it all together. So before I showed you here, this was a typical nucleated cell. Any cell in the body that has a nucleus will do this. We'll use MHC-I. That's not true of MHC-II. This is a specialized system for cells that can do phagocytosis. And so a cell, and this could be a dendritic cell, a macrophage, or a B cell, it will take in something from the environment. And it will ask this CD4 positive helper T cell, is this the protein you're designed to see? And this CD4 positive helper T cell will be asking, is this the protein that I'm able to see using my T cell receptor? And the interaction between the MHC2 and the T cell receptor is stabilized by the CD4 co-receptor. So a cell that has a CD4 co-receptor, you would know is going to be able to examine MHC class II molecules. So this is going to be a helper T cell, and it's going to look at what other cells have brought in from the outside. This could be a macrophage asking, is this thing in me? I ate it. Is it a deadly pathogen? And this helper T cell doesn't know the answer to, is it a deadly pathogen? But it knows the answer to, was I activated by another copy of that same protein? If so, whatever that is, it's all over the body causing an infection. So this will recognize it. There are a lot of different situations where this interaction happens between a phagocytic cell and a helper T cell. And we'll look at those in the next video.